This is part 3 of section 8.1. We've talked about sequences, we've talked about them in recursion form, we've talked about them in regular form, we've talked about factorials. Now we're going to talk about what we call summation notation. Sometimes we're going to be interested in what we get out of if we add the first certain number of problems in a sequence. It comes up a whole lot, okay? So the sum of the first n terms of a sequence is represented by the summation notation. Okay, this is a Greek letter. It is the capital letter for it's capital sigma, which is equivalent to the S in English. So S for sum, sigma, sum. Okay, this says we start. This is called I is called the index of summation, and it's our starting point. N, which is written up here, is called the upper limit of summation. And 1 is the lower limit of summation because we have I equal to 1. And here is a sequence. What this is saying is we're going to plug in 1, then we're going to plug in 2, and we're going to plug in 3, and we're going to plug in 4 until we get to this last number, whatever it is, and it stops. And then we're going to add them all up. And that's going to be the answer to our summation. Okay, so let's look at this first example. We have this sum from I equal to 1 up to 6. So I'm going to plug in the numbers 1 through 6, and then I'm going to add my answers together. So this is 7 times I, so 7 times 1, plus 7 times 2, plus 7 times 3, plus 7 times 4, plus 7 times 5, plus 7 times 6. I plugged in the numbers 1 through 6. This would be, if I were just asked to list the first 6 terms of this sequence, I would have these values after I do the multiplication. I'd put commas between them. But we're asked to add them together. So let's keep going. This is going to be 7 plus 14 plus 21 plus 28 plus 35 plus 42. And you could use your calculator, add all of these up, and you get 147. Okay? So that's how this notation works. Whatever this number is, that's the first number you plug in. Whatever this number is, that's the last number you plug in. You figure them all out, you add them together, you're done. Okay? So let's do the same thing for this sum. I want to start at 1, I equal 1, and I'm going to stop at 5. So I'm going to plug in the numbers 1 through 5, and then I'll do the arithmetic. So this is going to be, I start at 1, so 1 plus 2 factorial over 1 factorial, plus, plug in a 2, 2 plus 2 factorial over 2 factorial, plus 3 plus 2 factorial over 3 factorial, plus, plugging to 5. Okay, so 4 plus 2 factorial over 4 factorial. And then the last one, 5 plus 2 factorial over 5 factorial. Okay. So I'm not going to do these calculations here because like that problem where we first talked about factorials, we're going to have some cancellations, and so we don't need to do all of the arithmetic here. I'm just going to do the arithmetic inside the parentheses now. So this is 3 factorial over 1 factorial plus 4 factorial over 2 factorial plus 5 factorial over 3 factorial plus 6 factorial over 4 factorial, plus 7 factorial over 5 factorial. Okay, so this is the same thing as 3 times 2, and remember you could stop at any point and write the rest as a factorial, over 1 factorial, and your factorials are going to cancel out. So from this one, I'm going to do the arithmetic as I go. 3 times 2 is 6, plus, this is 4 times 3 times, let's do these in parentheses, that might help, times 2 factorial over 2 factorial. These cancel. 4 times 3 is 12 plus. So you can see what's happening here. I have 5 times 4, and I can stop at 3 factorial over 3 factorial. 5 times 4 is 20 plus. That's going to be 6 times 5 times 4 factorial over 4 factorial, and then the 4's go away. 6 times 5 is 30, plus 7 times 6 times 5 factorial over 5 factorial. 7 times 6 would be 42. And now add these up. 6 plus 12 plus 20 plus 30 plus 42, and this is equal to 110. Now, obviously, there is a pattern here, and you probably see it. I wrote out every single step because it's always better to have more in your notes than you really need. But this is how this problem works. You could do this in your calculator if you really wanted to, but usually it's going to help you to write down some of these steps. If you depend on your calculator too much, you may not recognize that you make a mistake, and you won't be able to find it because you didn't have anything written down. Okay? So let's do this one. I want the sum from I equal to 2, we're not starting at 1 this time, to 4. So I'm just going to plug in 2, 3, and 4. This is equivalent to negative 1/3 squared plus negative 1/3 cubed plus negative 1/3 to the 4th power. Now, we talked about having alternating signs earlier with a -1. Anytime you have a negative number raised to exponents that are just going up by 1 each time, you're going to have alternating signs, and we're going to have that here. Negative 1/3 squared, a negative squared is going to be positive, and when you have a fraction squared, you square the top and the bottom. 1 squared is 1, 3 squared is 9. Now this is negative 1/3 raised to an odd exponent, so this is going to be a negative number, and you cube the top and the bottom. 1 cubed is 1, 3 cubed is 27. Okay, and last you have negative 1/3 raised to the 4th power. It's an even exponent, so this is going to be a positive number. 1 to the 4th power is 1. 3 to the 4th power is 81. Now we need to combine these, and you can use your calculators, or you can find a common denominator. If I do 1/9 minus 1 over 27 plus 1 over 81, 1, I get 7 over 81. And that is your answer here. Okay, our last type of problem. This is difficult only if you make it difficult. What they've done is they've given us a pattern, and it is a sum, and they want us to go from this back to summation notation. Okay? And what they're telling us is they want us to start at 1, and we're supposed to use I as our index. Okay? So this is going to be, I know this much, the sum of I equal to 1 to something. Okay. Now I know I'm supposed to be plugging in the numbers 1, 2, 3, 4, 5, and so on. And I look here, the part that's changing every time is the base. So the number that's changing, the I, that's changing every time, but every time it's being raised to the 4th power. So it looks like I can do I to the 4th power. Now let's check this. This would be 1 to the 4th plus 2 to the 4th plus that's working. Okay. And then what is the last number we plugged in? If I start at 1 and I follow this pattern, the last number I plug in is a 12. So I can write this sum as the sum from I equal 1 to 12 of I to the 4th power. We're just going backwards. Okay? Now let's look at this one. This one is actually easier than the other one, even though it looks scarier because it ends in a variable here. We know we are supposed to do a sum from I equal to 1 to something of something. Okay? Well, we have a fraction here. Let's figure out what's changing every time. Well, it looks like I'm plugging in 1, and it looks like these are going up by 1. So my numerator is 1, then 2, then 3, and 4, and so on. So I have I in the numerator. Now, what's changing in the denominator? Well, the 9 is always there, so it's going to be 9. But the exponent is changing, right? Remember that 9, that can be 9 to the 1st power. And so it looks like we were plugging in 1, 2, 3, 4, and so on. So our exponent here is an I. Well, what is the last thing we plugged in? You look at your last term, and you can see that the last thing they plugged in is an N. Now, I said this is an easier problem than the one before, and that's because right here, all you have to do is to change these variables to i's, and you've got this part. The last thing they plugged in was a variable, and it's just a change of variables right here. That's it. That's the end of section 8.1.